Okay, this is going to be the motion second video. So here we're looking at distance time graphs, and you can tell a distance time graph from what's on the axes. So just make sure you look at these axes before you're going to do anything with a graph. So what's stationary? Well, stationary is stopped, okay, something like that. So you're not covering any distance for any time. So it could be across there, it could be across at 0, could be anywhere as long as it's straight across, because you're not increasing your distance as you increase your time. Now, constant velocity, if you're looking at constant velocity, you're going to be increasing your distance at the same rate each time. So if you do 1 meter for 1 second, then you're going to do 2 meters in 2 seconds. Okay, so we're going at a constant velocity. 3 meters will take 3 seconds. And if you could do that, you get a nice straight line at an angle. If you're going faster, constant speed or velocity, then you'll be at a steeper line. Slower, shallower line. Acceleration, deceleration. Okay, so let's say we're looking at acceleration first. Okay, what you're going to be doing is you're going to be increasing the amount of distance you cover per second. So let's break this into seconds. So 1, 2, 3, 4. Now if we cover in the first second that much distance, then we're going, well, it could be going constant speed, but in the second second we are now going to cover a greater distance. See, we've gone from that change to that change. Okay, so we've covered a greater distance in that second second than we did in the first, so we must be getting faster. And then if the next one's all the way up there, then you can see that a curve upwards is accelerating. That's a bit dramatic, that curve. It'll be more like that normally. Deceleration, you're still going to be increasing your distance, but the rate you increase it is going to get less. Instead of starting, if we started there, the next one is going to get shorter, 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 shorter for each distance. So in other words, it's going to curve this way. So the slope of this line shows how fast you're going. The greater the slope, the faster you're going. It's compared to this end where you're actually quite flat, you're not going hardly at all. Velocity time graphs. Okay, in this case we got stationary, so in stopped. Remember, you could actually have some numbers up the side here, 1, 2, 3, 4 and so on. So if we had anything up here, we must be moving. So we can't be up here. We must be along the 0. Okay, so it's stationary. Constant velocity. Well, remember, if we had numbers here, it's staying at that one number all time. So in this case it will be 2 meters per second, and we're staying at that velocity or speed all the time. Remember, we're looking at the top of the graph to see what type of graphs these are. This is velocity or speed measured in meters per second. Constant acceleration. So in this case we're going to be increasing our speed. So 1, 2, 3, 4. So we're going to be increasing up that way as time progresses. And we're going to do it at such a time that we'll have the same amount of increase in speed for every increase in time. So if we have 1 and 1, we might have then 2 and 2, 3 and 3. Or it could be 2 and 1, 4 and 2, and so on. And there'll be a nice straight line. Not like mine. Constant deceleration, then we're slowing down, we're decreasing our value, and because it's constant, the change per second is always the same. So it's a nice straight line at an angle down that way. Increasing acceleration, so we're getting faster, so we're raising our number up this side, so we're getting larger up that way, and the speed we're doing that is getting faster. So we're starting off slow, then suddenly go faster upwards per unit of time. So if we getting faster. Suddenly we get faster a lot quicker up towards that end. Okay, so we have covered a greater amount of speed change in that much time compared to here where we've only increased a little bit in that much time. Decreasing acceleration, well, we're slowing down our acceleration. So at all times, because of this word here, we're still going faster. Okay, so we're still going faster, but we're decreasing the rate we're going faster. So here I'm speeding up quickly, and then I start speeding up less over time. See, in this time there, I've only increased by a little bit. But however, if I look at this time here, I've increased all the way from there to there in that same amount of time. So there's a greater increase in speed here compared to there. And yet again, you could say that the slope of the line shows the acceleration. So here it's shallow and it gets steeper, so it's getting much larger acceleration. Here we're steep and we're getting shallower to show we're decreasing our acceleration. Acceleration time graphs. Okay, so this time for a constant velocity, well, what's the acceleration there is 0. We're not changing our acceleration at all, so it must be 0. Constant acceleration, okay, in other words, if we got a fixed value, we stay at it. Increasing acceleration, so it could just be any sort of line up or a curve. So, what you can find out from the graphs, we've already said that from a distance time, that a slope, that can actually tell you your speed, because remember, the greater the slope, the higher the speed. So gradient equals speed, or accelerate, or velocity, sorry. But if it's distance, it's speed. Velocity time graph, a slope, that will tell us your acceleration. The greater the slope, the greater you're increasing your speed per second. Area under the graph actually tells you how far you've gone. So for example, how far does the car go in the first 3 seconds? Well, this is a distance time graph, so all we have to do is read off there. We've gone 30 meters in that 3 seconds. Find the speed of the car in the first 3 seconds. Well, if we've done 30 meters in 3 seconds, you could say that speed is equal to distance over time, so it's 30 divided by 3, which equals 10. Now, another way of looking at that is we've just worked out the gradient of this line. Okay, so that's a slope, rise divided by run. Describe what happens between 3 and 5 seconds. Well, we're not changing our distance, so we must be stopped. Draw a line showing the motion of a different car that travels at half the speed of the original car in the first 3 seconds. So if you're going half the speed, you're going to have half the slope. Okay? In other words, your rise in the same time will be half the rise. Okay? So in other words, we're only going to get to 15 meters in that first 3 seconds. Okay, so looking at this problem, we could find out a few things from this. This is a velocity time graph, speed time graph. So we can see that we're increasing our speed here. So we've gone from 0 to 20 meters per second in 10 seconds. So time difference there, 10 seconds. So our slope tells us the acceleration. So it equals the slope, which equals rise over run. Gradient is a better word. Okay, so that equals 20 divided by 10 equals 2 m over s squared. What's the acceleration here? Well, there's no gradient, we're not increasing our speed, so it must be 0 m over e squared. The other thing that we can work out is the distance, and that's from the area. So that equals half base times height, so that equals half times 10 times 20, so 100 meters. Okay, this one here, well, that's just a rectangle, so that will be 30 is the length of it, 20 is the height. Okay, so you're looking at the area of this one equals 600. So if you want to know the distance covered to 50 seconds, it's just going to be 600 plus 100, which equals 700 meters. What's happening here? We're slowing down, but we're decreasing the rate we're slowing down. It's getting flatter. Okay, we've got towards the bottom of this curve, around there is no change in velocity over time, speed over time. However, there's a large change, so we're decreasing our deceleration. Okay, so an egg is dropped towards an unsuspecting student from the top floor of the science building. The egg flew 8 meters when it reached the student and had a velocity of 12.6 meters per second. Sketch a velocity time graph for the egg's motion. How much time does the student have to get out of the way? Okay, so let's say we're going to look at what's going to happen here. Sketch a velocity time graph. So remember v meters per second divided by time. Against time. Now, this thing's going to increase its speed until it gets to 12.6. And it's going to do it in a certain amount of time. We don't know the time yet. Now if we draw in the line, well, it's going to be a constant acceleration, okay, which is equal to g. Going along there. Now, what do we know? We actually know that the area under this graph is going to be equal to 8 meters. So, how do we find the size of this side of a triangle? Well, we know half base times height is going to be equal to 8. Okay, 8 meters. So, half times the base times 12.6 equals 8. So then we solve for the base, and you get about 1.27 seconds, something like that. Near the Earth, the gravitational field can be considered to be uniform. If a body is dropped in this gravitational field, its motion is called free fall. Okay, so it's falling freely. The acceleration of free fall for a body near the Earth is constant is equal to 9.8 meters per second. Or, you guys can use 10 this year. Okay, so it's a constant line and it has a gradient of around about 9.8 or 10. Okay, in other words, for every second, we're increasing our speed by 9.8. So, if we started talking about air resistance, then as you increase your speed, as we're falling down and we're getting faster, the actual air resistance, the force of air resistance gets larger, okay? And that actually means our acceleration will decrease, okay? Because the size of the force, the resultant force pushing down, gets smaller. So as the velocity of a falling body increases, the air resistance force also increases, hence the acceleration of the falling body decreases. Think of F equals ma. The resultant force, in other words, the difference between your weight and the friction, which is increasing. That one increases as you go faster, meaning that they're almost balancing out. The acceleration will continue to decrease until it reaches 0, at which point we say that the body has reached terminal velocity. And if you look at it, this is what we can get from the graph. Here we've got around about 9.8 meters per second. Okay, let's try a different color. Per second. Okay, so these are acceleration, pretty quick. Okay, you see your change in speed there is pretty high per second. Change in speed is getting less per second, so the air resistance has increased. Okay, so acceleration may only be something like 3 meters per second per second. Here we're at terminal velocity. Okay, so this thing has reached terminal velocity. Now what we have here is a sudden deceleration. Okay, so this could be like -10, oh, maybe more than that, probably. Let's say -100 ms to -2. Some large deceleration downwards. And then we find a new terminal velocity. And then suddenly we stop. Okay, really quickly. So this is like a skydiver. So this person is skydiving, and then the parachute opens and then hits the ground.